Hello students, welcome to YourPedia platform. My name is Arun Pathania and today in this video we are going to solve a question from the NPTEL assignments for the branch of Civil Engineering. Students, as we all know that the NPTEL assignments are very important. The questions in them are great practice for actual GATE exam or even some of the PSU exams. But it is very tiresome for a student to visit all these video lectures and find those assignment questions. So what YourPedia has done is that we have collected all these questions and then arranged them nicely in books like these. This is the book for Civil Engineering branch. We have other books for other branches also. You can visit on our website and purchase these books and start preparing. We have also prepared the video solutions for each and every question so that you can get benefited from there also. So what are we going to do in this video then? आज I have taken a question number 53 from the page 106 of this book. This question will be from the subject of structure analysis और मैं उस question को यहाँ solve करूँगा. I will also tell you the concept behind that question so that you can get an idea कि इस book में किस level के question आपको दिखेंगे. Okay, so let us just read the question. So the question is, we have to determine the deflection at the midpoint of this given simply supported beam. Okay, a beam has been given, sectional properties has been given. As you can see, the moment of inertia is not constant throughout the span of the beam. For this particular span it is I, for this particular span this is also I, but for this BC span it is twice of I, it is 2I. So flexure rigidity is not constant for the whole beam. There are number of methods through which we can find the deflection at certain point in beams like double integration method, strain energy method, moment area method, conjugate beam method, Macaulay's method. But when your flexure rigidity is not constant throughout the span, only conjugate beam method and strain energy method will be beneficial because other methods will be very lengthier and we don't want that. We want our answer to be convenient and to be quick. So we can either use conjugate beam method or strain energy method. There are a lot of, there is possibility of error in strain energy method during calculations. So I have taken the conjugate beam method, which is comparatively easier and faster. So how conjugate beam method helps us to find the deflection? Let me tell you this thing. First of all, we convert our real beam into a conjugate beam. Now what is this conjugate beam? The conjugate beam versus real beam, I'll tell you, the conjugate beam will have the same length as that of the real beam. So if our real beam is 6 meter in length, its conjugate beam will also be 6 meter in length. Second thing, but the supports in conjugate beam will be different. They will be the conjugate of the real support. As we take in matrices or in imaginary numbers, we take this conjugate term na. So real beam, real number gets converted into imaginary number. Same in that case, what happens is ki supports will be conjugate of the real supports. Third thing that separates the conjugate beam from the real beam is that the loading in conjugate beam will be equal to the M upon EI diagram of the real beam. Now what is this M upon EI diagram? We create the bending moment diagram of the real beam. We have that bending moment diagram. Now then we divide the ordinates, whatever the ordinates of this BMD diagram, we divide that with the flexure rigidity of the beam, and whatever is the resultant diagram, that is my M upon EI diagram. Then I take this M upon EI diagram and place it over the conjugate beam that we have made, and this serves as the loading for that diagram. Now after this, our conjugate beam is now complete. So why have we made this conjugate beam? What is the advantage? Because there exists a relationship between real beam and the conjugate beam. Now what is that relationship? That relationship is that if I want to find the slope at any point in the real beam, that will be equal to the shear force at that particular point in the conjugate beam. And you know how easy it is to find the shear force at a point in a beam? So by finding something easier, we have found something which is difficult to find. So because by using this relationship, so therefore this relationship is so important. Similarly, deflection at any point in the real beam is equal to bending moment at that particular point in the conjugate beam. So what we have to find, we just have to create the conjugate beam and we just have to find shear force and bending moment at certain location so that we can find the slope and the deflection at that corresponding location in the real beam. So you can see how easy, convenient and interesting it is. Okay. So let me tell you first about what are the conjugate supports. Okay, how we're going to replace the real supports with the conjugate supports. So now these are the real beams supports. You can have a fixed end support. You can also have a like free end in the real beam. You can have a pin support or hinge support, a roller support. You can have internal hinge, intermediate support here. So what are the conjugate supports of these real beam supports? Let me tell you. So first, we know that there is a relationship between the slope and the deflection of the real beam and the shear force and the bending moment of the conjugate beam respectively. So we are going to use this relationship and we are going to find the conjugate beam supports for the real beam supports. So यहाँ पर क्या है, we have a fixed support. हमें पता है कि at the fixed support the slope will be equal to 0, the deflection will be equal to 0. So इसका जो conjugate support होगा in the conjugate beam वो एक ऐसा support होगा at which the shear force will be equal to 0 and bending moment will be equal to 0, because there is a relationship between the slope and shear force and deflection and the bending moment. So what is that support? What is that thing जहां पर shear force भी 0 हो और bending moment भी 0 हो? That is a free end. ठीक है, तो हम इसको replace कर देंगे free end से. A fixed support in the real beam will be replaced by a free end in the conjugate beam. So अगर हमारे पास एक कैंटिलीवर है जिसका एक एंड फिक्स्ड है, तो conjugate beam जब उसकी बनाएंगे तो ये जो फिक्स्ड एंड होगा वो फ्री हो जाएगा, वहां पर कोई भी सपोर्ट नहीं रहेगा. ठीक है, देन अगर फ्री एंड आया, अब कैंटिलीवर का दूसरा एंड तो फ्री है, तो उसको कैसे चेंज करेंगे? If there is a free end, at the free end there will be some value of slope, there will be some value of deflection. So we need to replace it by a support where there is some value of shear force also, there is some value of bending moment also. And what is that support? That support is fixed support, because fixed support पे shear force will be there also and there is the fixed end moment also. So इसको replace करेंगे एक fixed end के साथ, एक fixed support के साथ. So you can see एक कैंटिलीवर अगर मेरे पास है जिसका यहाँ फिक्स सपोर्ट है और यहाँ फ्री एंड है, तो अगर उसका कॉन्जुगेट बीम बनाएंगे तो वो बनेगा यहाँ पर फिक्स सपोर्ट और यहाँ पर फ्री एंड. इट विल स्टिल बी ए कैंटिलीवर, लेकिन जो लोकेशन है वो इंटरचेंज हो गई है सपोर्ट्स की. ओके, देन इफ आई हैव ए पिन सपोर्ट, फॉर एग्जांपल मेरे पास जो है एक सिंपली सपोर्टेड बीम है, एक तरफ पिन सपोर्ट है, एक तरफ जो है वो पिन सपोर्ट है, हिंज सपोर्ट है, एक तरफ रोलर सपोर्ट है. ये दोनों पिन सपोर्ट की कैटेगरी में आ सकते हैं. ठीक है, अब क्या होता है पिन सपोर्ट पे? व्हाट हैपेंस इज वी हैव सम वैल्यू ऑफ स्लोप बट देयर इज नो डिफ्लेक्शन, डिफ्लेक्शन इज 0. सो वी नीड टू रिप्लेस इट विद अ सपोर्ट जहां पर शेयर फोर्स की कुछ वैल्यू हो बट बेंडिंग मोमेंट नीड्स टू बी 0. सो व्हाट इज दैट सपोर्ट? दैट इज हिंज सपोर्ट और पिन सपोर्ट ओनली. सो दिस हैज टू बी रिप्लेस्ड बाय दिस, आइदर दिस और दिस. सो आई कैन से कि मेरे पास अगर एक सिंपली सपोर्टेड बीम है जिसके दोनों सपोर्ट्स जो होंगे दैट विल बी पिन सपोर्ट एंड हिंज सपोर्ट, तो एट दिस विल बी रिप्लेस्ड बाय दिस ओनली. सो दैट सिंपली सपोर्टेड बीम विल रिमेन सेम इवन आफ्टर we create the conjugate beam. Simply supported beam will remain same only. So in this question we have simply supported beam. So when we create the conjugate beam, the length will also gonna remain same and the supports are also gonna remain same. Okay. Next is basically what if we have an internal hinge. At internal hinge, theta is also not equal to 0, deflection is also not equal to 0. So we need an intermediate support where bending moment is also not equal to 0 and shear force is also not equal to 0. We can't use a fixed support in between ना. So यहाँ पे fixed support नहीं आ सकता. Fixed support पे भी bending moment is not equal to 0 and shear force is also not equal to 0. But that is an external support. It cannot be an intermediate support. So इस case में we are going to replace it by an intermediate pin support. Okay, and again if we have an intermediate pin support in the real beam, it will be replaced by an internal hinge in the conjugate beam. So in this way these real beam supports will be replaced by these conjugate beam supports whenever we make the conjugate beam. Now we have also done the supports. Next thing is we have to talk about the loading of the conjugate beam. So in order to make you understand this thing in a better way, let me take a real example. So this is our given beam. I'll prepare the BMD diagram for this beam and then I'll create the M upon EI diagram out of it, and then I will use it as loading on the conjugate beam. So you can understand it in a real time way. You can understand how practically we use it. Okay. So first of all, in order to make the BMD diagram, I have to find the support reactions first. Now as you can see, it's a symmetrically loaded simply supported beam. So in case of this symmetrically loaded simply supported beam, what happens is that both the reactions are going to be equal to one another. This is an additional information that we know. Okay, that both the reactions will be equal to one another. Now we are going to use the equilibrium equation. First is the summation of Fy is equal to 0. So all the positive forces are, all the upward forces I am taking to be positive. So Ra plus Rd will be positive and 20 kilonewton will be taken as negative. So from here I can write that RA plus RD is equal to 40 kilonewton. Okay, this much I can write. Now since RA and RD are going to be equal, so I can write 2RA is equal to 40 kilonewton, and from here I can further simplify it into that RA will be equal to 20 kilonewton. Now since RA and RD will be equal, so RD will also be equal to 20 kilonewton. So this value RA will be 20 kilonewton and this RD will also be equal to 20 kilonewton. Now I have to create the bending moment diagram. For that I have to write the bending moment equation so that my bending moment diagram would be clear to me, and I also know how the variation is. Is it linear variation, whether it will be constant, whether it will be second degree variation. So for that it is better to write the bending moment equation. But if you are comfortable enough that you can draw the bending moment diagram without writing the bending moment equation, it is up to you. Okay, so first I have to take a section. So let me take a section, section 1-1. Let me take a section 1-1 in this AB span. First I am writing the bending moment equation for AB span. So I have taken this section 1-1, which is at a distance of x distance from the point A. So I can write the bending moment equation for this section 1 will be equal to RA into x. As you can see, this RA will create a clockwise movement at this section 1-1 from the left side, so it will be positive bending moment diagram. It will be positive bending moment. So it's become plus RA into x. The value of RA is 20, so it becomes 20x. So this is the equation when x belongs to A to B, or the numerical value of x is 0 to 2 meter. So when this equation is satisfied, when x is between this range, then this is the bending moment equation. When x is in another value or is another section, then this will not be the bending moment equation. Okay, this is only valid when it is in this range. So from here I can find the bending moment at point A. Obviously you can see bending moment at point A is going to be 0 because it's a pin support. But we can also verify it from this equation. Here I have to put x is equal to 0, so this becomes 0. Okay, so you can also have also cross-checked from here. As you can see, the value of the power of x in this case is 1. So there will be linear variation in this span. ठीक है, straight line variation होगी bending moment diagram की. And we can also find the bending moment at point B where x is equal to 2 meters. So I can write 20 into 2. So at point B, the bending moment will be positive 40 kilonewton per meter. Similarly, I can find in this particular span, in CD span. Now this is I have taken the section. I am writing the bending moment from the left side. Now in this case, if I am writing the moment from the left side, too many forces, I can write the bending moment equation from the right side, and there will be only one force here. So what I am doing that is I am doing a section, say section 2-2, which is at a distance of x meters from the D support, and now I am writing the bending moment equation from the right side. So I can write bending moment equation for section 2-2. This now will be equal to, let me use another color, this now will be equal to RD creating an anti-clockwise moment. So anti-clockwise moment to the right of the section will be taken as positive bending moment, sagging bending moment. ठीक है, तो 20 kilonewton into x, so plus 20 into x. ठीक है, plus 20 into x. This is my bending moment equation for this particular section. This is valid when x belongs to D to C or 0 to 2 meter. When the value of this is this, so in this particular span, this equation is valid. In this particular span, this equation will be valid. Okay, now from here I can find I know the bending moment at point D will be equal to 0 because hinge support. I can find the bending moment at point C now. Bending moment at point C will be 20 into 2, which will be plus 40 kilonewton meter. So bending moment at point at point C and point B will be equal to one another and is equal to 40 kilonewton. Now I have to find for the middle span, BC span. So now for BC span, I'll again take a section, let's say section 3-3. I'm taking, and now this section 3-3 is, I'm again saying that it is at a distance of x meter from the point A. Okay, now this x is not into consideration because this section I'm not talking about, I'm talking about this section, and now this section is at x meter distance from point A. Okay, so I can write the bending moment at point 22 will be equal to, there will be RA, positive RA at a distance of x. As you can see, there will be this RA reaction which will be creating a positive bending moment diagram for, on this point, this 3 section, and what is the distance between this force and this section? X distance. Okay, now what is another force that is also creating moment over here, and that force is this 20 kilonewton. Now this 20 kilonewton is creating anti-clockwise movement to the left of the section, so negative bending moment it will be taken. Okay, so what is the distance between this force and this section? This is 2 meters, this hole is x meters, so what is this distance? X minus 2 meters. So I can write minus 20 of x minus 2 meters. So this becomes 20 into x because the value of RA is 20. 20 minus x minus 20x plus 40. I can write this. This will cancel out. This becomes 40 kilonewton meter. So from here we can see that this is valid when x belongs to B to C or 2 meter to 4 meter. So from here I can see that in span, BC span, the variation of bending moment will be constant because there is no value of x here. So it will not be linear or parabolic or anything, it will be constant. It will have the same value of 40 kilonewton. So from these three equations, I can now draw the bending moment diagram. Okay. So let me draw the bending moment diagram. What will be my bending moment diagram will look like? So say this is my span. Okay, this is my point B, this is my point C, point A, and this is point D. Okay, so now for up to point B, at point A bending moment was 0, at point B bending moment was 40 kilonewton meter, and there is a linear variation and it is positive, so it will reach like this. This value is 40. At point D bending moment was 0, at point C again bending moment value was equal to 40, and there is a linear variation here also. In BC span bending moment was constant and the constant value was 40, so it will be like this. So this is my bending moment diagram for this particular span. Now from here I can draw the M upon EI diagram by dividing the ordinates, these ordinates, by the flexure rigidity of corresponding span. So I can so say this is my beam, this is point A, this is my point B, and this is my point C, and this is point D. So in span AB and CD, the flexure rigidity was EI only. As you can see, flexure rigidity in this span is EI only, but in this span it is 2EI. So I have to divide by 2EI, and for these spans I have to divide by EI. So it will remain same only. So as you can see, for these span it will be 40 upon EI. This span it will also be 40 upon EI. But in this case, the ordinate will be divided by 2EI. So this will become half. So यहाँ पर bending moment was 40. So what will be bending moment at point B? Now, what will be the ordinate? Ordinate will be 20 EI. At this point, the ordinate will be of M upon EI diagram will be 20 by EI. This will remain constant. Here also 20 upon EI. Now I have to join these points, and there will be this drop at point B and point C, as you can see. So this is my M upon EI diagram, positive M upon EI diagram for this particular beam. If flexure rigidity were constant, then इसी को ही मैं EI से divide कर देता, इसके नीचे EI कर लगा देता, and this will become the M upon EI diagram. But in this case, since flexure rigidity same नहीं थी, ये वाला जो portion था that was thicker, that has higher value of moment of inertia. So यहाँ पर क्या हुआ कि ordinates जो हैं वो हमें reduce करने पड़े in order to use the conjugate beam method properly. So मेरे पास अब M upon EI diagram भी मिल गया. So मेरे loading is also sorted और जो मेरा conjugate supports हैं वो भी मेरे को पता है, length भी मेरे को पता है. So now I can draw the conjugate beam and use the relationship between deflection and shear force, slope and shear force, deflection and bending moment. So let me draw the conjugate beam now. So the conjugate beam for this given simply supported beam will look like, supports will remain same as I have already told you earlier. Supports जो हैं वो same ही रहेंगे, length भी same ही रहेगी, ठीक है. It will be 2 meters, it was 2 meters earlier, 2 meter, this span was 2 meters, and this will also remain 2 meters. So this was point A, this was point B, this is point C, and this is point D. It will remain same, but the loading will be m upon ei diagram. So loading के लिए क्या हो जाएगा कि जो हमारा m upon ei diagram था उसको हम लोग यहाँ पे बना देंगे. And since it was positive, so now loading will go upwards. Loading will point upwards rather than downwards. जैसे हम normally in beams we see the problems that we solve, we see that the loading is downwards, but in this case since m upon ei diagram was positive, so positive यहाँ पर जो है is upward direction, we have taken positive ना, so here the load will point out upwards. If it were a negative bending moment diagram, then load would have pointed out downwards. Okay, so what we are going to do, and what is this value? This value is 40 upon ei. This value is 20 upon ei. Again this value is 40 upon ei. So what we can do for convenience, we can divide this loading into three portions. So first is my this triangle that I have taken. Again this is my rectangular portion that I am left with from point B to point C. Since I have to find the deflection at point E at the midpoint, so I have to find the bending moment at this point. So let me do what I have to do, that let me mark point E also. Point E को भी मैंने mark कर दिया, and then I rectangular जो ये हमारे पास portion है इसको भी मैंने दो parts में divide कर दिया. ठीक है, this is part 1, this is part 2. So इसको मैंने 2 बोल दिया, इसको मैंने 3 बोल दिया. ठीक है. Now what is this distance? This distance is 1 meter. This distance is 1 meter. This is my triangular portion, ordinate 40 ei and base length is 2 meters. This is rectangular portion, ordinate 20 ei, base 1 meter. Same for this case. अगर ये जो triangle है ये same as this. So this is my fourth portion, I can write. ठीक है. So this is my RA, this is my RD. First I have to find the support reaction, then I can find the bending moment at any point. Okay. What I have to do is I have to find the theta E in the real beam. This was my question. This was asked. Now this theta E in the real beam, from our relationship that we have developed, we can write that this will be equal to bending moment at point E in the conjugate beam. In the conjugate beam. So for finding the bending moment at point E, first I have to find the support reactions because their value will be required. Now how I can find the support reaction? First, as you can see, it's a simply supported beam and a symmetrically loaded simply supported beam. From the midpoint if I see, this is the same thing, this is the same thing. So it's symmetrically loaded. So what relationship I told you about the symmetrically loaded simply supported beam? That both their supports are equal to one another. So in this case also RA will be equal to RD. Now I'll use the basic equilibrium equation of summation of F upon Fy is equal to 0. From here I can write plus RA plus RD. Now this loading is also upward, so this loading will also be positive. So it will become, now for this portion I'll find the loading first, equivalent loading. This will be 1 by 2. What is this? 2 meters. What is this? Ordinate 40 by EI. Now for this particular portion I'll find what is the value. This is 20 EI, ordinate is 20 EI. This base distance is 1 meter. Now what I am doing is, since this portion is exactly similar to this portion, I can do the 2 times of this and 2 times of this. Rather than writing the whole expression over again, I can just multiply these both loads by 2 because this portion is exactly similar to the this other portion. So what happens is, now I can write the equation. I have RA plus RD plus this becomes 80 EI, 80 upon EI, this becomes 40 upon EI. So this becomes 120 upon EI. And since RA and RD are equal, so I can write 2 RA is equal to minus 1 by 20 upon EI. So from here I can write minus upon 60 EI, and RD will also be equal to minus upon 60 by EI. So this is the value of my support reactions in this case. Both the support reactions will be equal and their value will be equal to minus 60 upon EI. So I can this I can correct the direction. Since it is minus, I can correct the direction. It means the value of RA is 60 upon EI but in downwards direction, and the value of RD is also 60 upon EI but in downward direction. Now I have to find the bending moment at point E. I have to write this. So how can I do this? Either from the left side or from the right side. So if I am doing from the left side, this will create an anti-clockwise moment taken as negative. What is the distance from point E? 2 meters plus 1 meters, 3 meters. So I can write that the bending moment at point E will be equal to minus of RA, which is what is the value of RA? Minus of 60 upon EI into what is the distance? 3 meters. 2 plus 1, 3 meters. What is the next force that I have to take into consideration? This I have taken into consideration. Now this force, this triangular portion. This triangular portion is creating a clockwise movement to the left of the section. So positive bending moment. Now what is the value of force? Then I'll find the value of the distance. So force is 1 upon 2 into 2 meter into 40 by EI plus 1 upon 2 into 2 meters into 40 by EI. Now what is the distance between the, now this force, the equivalent point load of for this particular loading will act at its centroid. Now what is the distance of the centroid from this longer side? It will be B by 3. So it will be 2 by 3 meters. 2 by 3 is equal to 0.67 meters. So this portion is 0.67 meter. This is 1 meter. So this total distance becomes 1.67 meters. So I can write 1.67 meters. Okay. Next force I have to take into consideration. Now up to this portion, now this rectangular portion I am taking into consideration the portion represented by term point, the second load that we can see, the second portion. Now this portion will create a clockwise movement again, so positive. What is the height? Height is 20 EI, base is 1 meter. So this will be plus 20 EI into 1 meter. And what is my perpendicular, what is my distance? So centroid will lie over here and the distance is half of this 1 meter, 0.5 meter. So this will be 0.5 meter. So this is my value of bending moment at point E. So I can solve this and I can find the value. This will be equal to 40, 67 and this will be 10. So this will become minus 180 upon EI. This will become plus 10E upon EI, and this will become 40 into 1.67, it will be 67 something, 67 point something upon EI. So this will give me, let me take the calculator, this will give me 40 into 1.67. 66.8, yes, around 67 it will come. So if I add this, I'll get 180 minus 70 is 6. So this will come out to be minus 103.2 upon EI. So this is my value of the bending moment at point E. So since bending moment at point E was equal to, will be equal to, this value will be equal to the deflection at point E in the real beam. So my deflection at point E, this is what I wanted to find in the first place. Now, so this will be equal to minus 103.2 upon EI. Okay. Now I can substitute the value of EI. I can find the value, this value in meters or millimeters. So first I have to take the value of EI. So value of E. So value of E is basically 200 GPa and value of I is equal to 10 raised to 8 into 10 raised to power 6 millimeter 4. So first is I have to convert this into standard values. So E is equal to 200 GPa gigapascal and value of I is equal to 8 into 10 raised to power 6 millimeter 4. Now please note the following conversion that I'm going to do with carefully so that you can understand what is happening. First of all, whatever loading that we have taken, whatever we have done was in kilonewton. Loading was in the initial beam, in the real beam, loading was 20 kilonewton, 20 kilonewton. We didn't convert into 20,000 Newton. So we have done all our calculation with distances being in meters and loading being in kilonewton. So this kilonewton and meter are basically our desired units. We have to convert these into the terms of kilonewton meter. Okay, not Newton meter, kilonewton meter. So this will become 200 into 10 raised to power 9 Newton per meter square. I can also write it as 2 into 10 raised to power 11 Newton per meter square, or 2 into 10 raised to power 8 kilonewton per meter square. So I have brought this into these terms, into kilonewton and meter. Similarly, I am going to bring the I value into kilonewton meter, since there is only length involved, so it will come into meter only. Okay, so this becomes 8 into 10 raised to power 6. Millimeter is basically 10 raised to power minus 3 meters, and the raised to power 4, so I also have to raise this to power 4. This will become 10 raised to power 6 into 10 raised to power minus 12 meter 4. So this I can write as 8 into 10 raised to power minus 6 m raised to power 4. So this is the value of I in standard units. This is the value of E in standard units. From here I can write EI is equal to this into this. This becomes 16 into 1600. This becomes 1600 only. Yes, this becomes 1600 kilonewton meter square. So in standard terms I can write this 1600 kilonewton meter square. So from here I can write that my deflection at point E in the real beam will be equal to minus this divided by 1600. So what is this value? 103.2 divided by 1600. So this value will be 0.0645 meter. Deflection will be in meter, standard value is meter here. So, and negative sign symbolizes that your deflection is downwards. Magnitude of that deflection will be this, and this will be, and if in millimeter I have to write this, this will become 64.5 millimeter. Now I'll have to check the alternatives at which option was correct. So as you can see, all this option is correct. 64.6 millimeter is given, and we have found 64.5. So it is very much closer to this option number C. So this option number C is correct. So now in this way you saw that we used the conjugate beam method, and very easily we converted the real beam into conjugate beam, and then we used the relationship between the slope and the shear force and the deflection and the bending moment, and from here we found the deflection at the point E very easily in the real beam. Now if we were using any other method, like say moment area method or double integration method, this will be a very lengthier process because the value of EI is not constant. So you can always use the conjugate beam method, which is a very easy and convenient method, and you can find the value of slope and deflection at any point, any desired point. Okay. So I hope that you have you might have found this video useful and helpful, and I wish you all the best in your future endeavors. Thank you. That's it from my side.